Okay, now you should work this for 4 flips and 5 flips. Use the same reasoning. Make sure you understand that reasoning before you look at the results. In any case, now for 4 flips, there are one way. If you list the sample space, you can easily count the number of ways to get no heads. That's 1. Number of ways to get 1 head is 4. 2 heads is 6. 3 heads gives you 4. 4 heads, 1. You can draw a tree diagram, trace the tree diagram, list the sample space, count them, or go to the Pascal's triangle, 1, 4, 6, 4, 1. You don't want to do, for example, Pascal's triangle unless you understand this and this. Because if you do, you don't really understand what these numbers are representing. They're just numbers that you put down, and you're not connecting yourself to the phenomenon of 4 flips, filling 4 slots, each with a head or a tail, etc. In any case, we do get this frequency distribution. So we can draw a histogram representing this frequency distribution. For 0 heads, we have 1 outcome. For 1 head, we have 4 outcomes. For 2 heads, we have 6, and so forth. Then we can also draw a bell-shaped curve that nicely emulates this distribution. We can do the same thing for 5 flips. Now I'm not going to give you the numbers. You should be able to work this out yourself and verify that this is what the histogram would look like, and that we can again sketch a nice bell-shaped curve to approximate this distribution. Now what I want to do then is I want to calculate the standard deviation of each of these distributions. And actually I'm just going to calculate the one for 3 flips. You should then do the calculation for the 4 flips and the 5 flips. I'll probably do one in an extra video, supplementary video, for 10 flips. We'll see what that looks like. Okay, so here's your frequency distribution. Here's your X, here's your frequency. Okay, frequency is a number of ways, so I'm just repeating this table here. Now I'm just doing this for the 3 flip case. So I have 0, 1, 2, 3 heads with frequencies 1, 3, 3, and 1. You should understand what that means. Okay, how do we calculate the standard deviation? Well, first we need to find the mean. Remember, the standard deviation, the standard deviation of a distribution or of any set of numbers is the square root of the mean of the squared deviations, where mean kind of has a little quotation mark around it if there are fewer than 30 numbers in the distribution. And we'll remind ourselves of what that means when we get to it. First thing you need is to find the deviations. But to find the deviations, well, deviation is the deviation of the result from the mean. We've got to find the mean. Now, for this distribution where we have only 8 possible outcomes, we could write down, okay, this distribution tells us that we've got 0 once, that we've got 1 3 times, so there are 3 1s in this distribution, that there are 3 2s, so we've got to write down 3 2s, and of course there's 1 3. We could easily add these numbers up. 0 and 1 is 1, and 1 is 2, and 1 is 3, and 2 is 6, 2 is 5, and 2 is 8, and 2 is 5, and 2 more is 7, and 2 more is 9, and 3 is 12. So that these numbers add up to 12. A more compact way to do this is say, well, we got 0, and I don't want to add up 1 3 times. 3 1s I know is 3, so just add the 3, I get 3. 3 2s is 6, I add that to the 3 I've already got, I've got 9, and 3 more makes 12. Now, the latter is a strategy we use when we have a frequency distribution. We have 1 0, of course that just gives us a 0. There's our 0. We have 3 1s, so we multiply 3 times 1 for the very reason that if we listed this out, we would have 3 1s, and we could then multiply that by 3 to see what that's going to contribute what that's going to contribute to the sum. Okay, and then we have our 3 2's, right there they are. We just do what we did. 3 times 2 is 6. Frequency times your x, 3 times 2 is 6. And 3 times 1 is 3. We add these numbers up, we get 12. We add these numbers up, we get 8. That's the total number of numbers that we have, or that we would have if we listed them all. That's the total number of possible outcomes. We divide that 12, the total, by 8. We get 1.5. That's our mean. Now that we have our mean, we can calculate our deviations. Now we can kind of look at it this way too. Here's our distribution. Where's the mean? Now, most people in class, or at least a couple of people in class, and these were people that usually get things right, said the mean was 2. So I asked, okay, well, if we balance this thing here, is it going to balance, or is it going to tip one way or the other? Well, we can see that for 2, there's more of the distribution to the left than there is to the right, and this would clearly tip this way. So 2 isn't the mean. Now, as I was explaining that, one of the people said, oh, it's okay, it's 1.5, and that's exactly right. If we go there, then we're right in the middle, so the mean should be 1.5, and of course, that's what we got. But there's a pictorial representation of that fact. So, we calculate a deviation. How much does 0 deviate from the mean? Well, it's 1.5. Right there it is. This is not a disembodied calculation. It means something. It means that this result is that far from the mean. So, 0 is 1.5 units from the mean. How far is 1 from the mean? Well, the mean is 1.5. That's only half a unit there. Of course, we can do the arithmetic. We can subtract 1 from 1.5, and we get 0.5. That's how far this is. And if we subtract 1.5 from 2, we get 0.5. That's this distance. That's this deviation. And then 3 is 1.5 units from 1.5. We subtract 1.5 from 3, and we get our deviation 1.5. Now, calculating a standard deviation, which again is the square root of the mean, quote mean, of the squared deviations. We got squared deviations. We have to square our deviations. Well, it's easy to square. 1.5 squared is 2.25. 0.5 squared is 0.25, etc. Then what? Well, we could list the deviations. Now, we don't want to just add up these numbers because there are 3 of these, and there are 3 of these. Now, there's just 1 of these and 1 of these, but there are 3 of these and 3 of these. We could list the deviations, the 8 deviations, just as we have, and we understand that if we did that, we would have 3 of these, so we would multiply this by 3, add that to this one, multiply this by 3, and add that to the result, and then add this one. So we, in constructing our table, we do our squared deviation multiplied by the frequency. Okay? 2.25 occurs just once, so that gives us 2.25. 0.25 occurs 3 times, that gives us 0.75. Same for this 0.25. It occurs 3 times, we get 0.75. 2.25 occurs just once, so we just write that down once. We add these up, we get 6. We calculate our quote mean deviation squared, and it was very good. People in class remember that we subtract 1, and people pretty much remembered bits and pieces of this process. I think some people that didn't speak up really remembered the whole thing, but it was very good that people chimed in and say, okay, we got square deviations, we got to do this, and so forth. Okay, we get the mean deviation squared. We divide 6 by not 8, but 8 minus 1, because we have fewer than 30 numbers here. Okay, we don't have 8 numbers. We divide that, we get 6 over 7, which is about 0.86. And then we calculate the standard deviation by taking the square root of that mean of our squared deviations. And I think that's 0.94. It might be 0.93. You can check out all my arithmetic and make sure it's correct.